Hey everyone, we all get that thrill, right? When a new, massive model drops. But then, reality hits. And the question we all face every single day is, how do we actually get that power out of the lab and into the hands of our users? Well, today, we're going to dive into a super practical technique that makes it possible. We're talking about knowledge distillation. You know the feeling? We've all been there. A new state-of-the-art 70 billion parameter model is released. And it's incredible. It can reason, it can code, it feels like a total game changer. But then you look at the specs, and your heart sinks a little. You're thinking, how on earth am I going to get this thing into production without bankrupting my entire company? Right? That massive gap between the potential and the deployment, that's exactly what we're here to solve today. When you try to deploy these absolute giants, you hit a wall, a production wall. The hosting costs, they're astronomical. The inference latency, it leads to a terrible user experience. And the VRAM requirements, they're just not feasible for most applications we build. This is the challenge that distillation was born to overcome. All right, section 1, let's meet the teacher and the student. This is really the elegant solution to that billion parameter problem. So the whole solution is this really cool concept called knowledge distillation, and it all boils down to a super simple intuitive metaphor, the teacher and the student. So what is it? Put simply, knowledge distillation is a technique where we take a compact student model and we train it to mimic a much larger teacher model. The whole idea is to transfer its capabilities into a smaller, way more efficient footprint. You start with a huge, expensive, but incredibly smart teacher model. Then you train a much smaller, much nimbler student model. But here's the key. You don't just train it on the raw data. You train it on the wisdom of the teacher. The goal is to basically pour the teacher's intelligence into a package that's actually, deployable. And this table really highlights that core trade-off perfectly. You've got the teacher model. Large, complex, expensive to run, slow inference. It's our source of knowledge. On the other side, you've got the student model. Small, efficient, cheap to deploy, and fast. This is our production workhorse. We're literally capturing the essence of the teacher, but in a form factor that actually works for the real world. So what's the payoff? Why do we do all this? Well, it's huge. Distillation directly attacks all those problems we talked about with the production wall. We slash latency and costs. We enable things that were just pipe dreams before, like on-device and edge AI. This enhances user privacy, which is massive. It makes advanced AI accessible to everyone. And hey, it even reduces our environmental footprint. It's a win-win-win. Okay, moving on to section 2. How do we actually transfer this knowledge? The secret sauce here is unlocking a concept that sounds kind of mysterious, but it's incredibly powerful. We're talking about unlocking dark knowledge with something called soft targets. So let's start with how we normally do things. In conventional training, we use what are called hard labels. This means there's just one single correct answer. We show the model a picture of a dog, and we tell it the answer is dog, right? It's a one-hot encoded vector. 0 for cat, 1 for dog, 0 for car. We're only teaching it what is right. We're not teaching it why it's right, or how dog might relate to cat. All that juicy nuance is just gone. But with distillation, we shift from those hard labels to soft targets. Now, instead of a single right answer, we ask the big teacher model for its full probability distribution. It reveals how the teacher actually thinks. So it might say, look, I'm about 70% sure this is a dog, but, it has some kind of cat-like features, so I'll give that a 10%. And it has a little bit of a car vibe, so maybe 20% there. That extra relational information, that is the dark knowledge. It's an incredibly rich training signal for our little student model. And the training loop itself is surprisingly straightforward. Seriously. Step 1, you get the teacher's logits, its raw predictions, and remember, the teacher is frozen, we don't touch it. Step 2, you get the student's logits. Step 3, you calculate a combined loss function that basically tells the student, hey, be more like the teacher, and also get the right answer. Step 4, you backpropagate that loss, and step 5, and this is crucial, you only update the student model. That's it. We are just pouring knowledge from one vessel into another. All right, section 3. Let's look at a case study, the DeepSeek flywheel. Because that's all great in theory, right? But does this stuff actually work in practice? Let's check out a super powerful, real-world example from the DeepSeek team that proves, without a doubt, that distillation absolutely delivers. So DeepSeek created this absolutely brilliant flywheel. It's a 3-step process. First, discover.
They used super expensive, resource-intensive reinforcement learning to discover incredible reasoning abilities in a giant teacher model. Then, generate. They use that teacher model like a data factory to generate a massive dataset of high-quality, chain-of-thought reasoning examples. And finally, disseminate. They used all that synthetic data to efficiently disseminate or distill that knowledge into much smaller, actually deployable student models. It's an amazing, scalable way to democratize these really elite AI capabilities.
And here's the part that's truly profound. They found that, quote, the knowledge encapsulated in the text of the reasoning traces is largely independent of the model's internal structure. What does that actually mean? It means the knowledge they captured in just plain text was so powerful that they could distill it into completely different model architectures, like Llama and Quen. This is huge. It proves that the reasoning capability itself can be transferred, not just a specific model's weights.
And the results? Honestly, they're staggering. Just look at this. The distilled model, a 14 billion parameter model, significantly outperforms a state-of-the-art 32 billion parameter model. Let that sink in. A model that is less than half the size is quantifiably smarter on the target task. That right there is the power of distillation. Okay, last section. Section 4, your distillation playbook. This is what you need to get started. So at this point, you're probably sold on the idea. But the big question is, how do you actually do this yourself? Let's shift gears and get into a practical playbook for what you're going to need. First things first, let's talk hardware. Because, let's be real, the VRAM requirements are no joke. Take a look at this table. Even a small distillation, going from a 7 billion parameter teacher to a 1.5 billion student, can need somewhere around 40 to 60 gigs of VRAM. We're talking 2 high-end consumer GPUs right there. And this really highlights the key economic dynamic of all this. It takes an expensive cluster to create the distilled model, but the student you get at the end, that can run on cheap, accessible hardware that you can actually deploy. All right, to save you some major headaches, here are a few key best practices and pitfalls to avoid. First, a big do. Use an offline approach. Pre-compute your teacher's logits. It is way more efficient, trust me. Also, consider starting with a strong, already distilled model if you can. Now for the avoids. Avoid a student capacity mismatch. Don't make your student so small it can't possibly learn the concepts. Avoid a flawed or overconfident teacher. And of course, avoid a big domain shift between the teacher's data and your actual task. You know the saying, garbage in, garbage out? It absolutely applies here. So look, if you only remember one thing from this whole talk, let it be this. Distillation is the critical bridge. It's the thing that closes the gap between mind-blowing, state-of-the-art research and practical, real-world deployment. It is how we, as developers, take the insane power of these massive models and actually put them to work in our products and for our users. Ultimately, this is the key. It's the key to making advanced AI accessible, making it efficient, and eventually making it ubiquitous. So the question I really want to leave you all with today is this. What amazing, powerful, too big to deploy capability are you going to be the one to distill and democratize for the rest of the world? Thank you so much.